Instead of calling this x, I just wrote x over here, but because we have already used x in the question, I don't want to repeat x over here. So let's use the quantity y1 because it is corresponding to n1. Y1 is equal to 2. Okay, then for n2, n2 is 21. 21 y2 is congruent to 1 mod 5. Very simple actually. What is the inverse? 1. Yes. Okay. So y2 is 1. Then for n3, n3 is 15. 15 mod 7. This is a very simple example. 15 mod 7. Sorry. Uh, yeah, this is not I want to write. 15 y3 is congruent to 1 mod 7. Y3 is again 1. We'll solve a slightly harder, different example later. So the solution is x is equal to y1 multiplied by the first modulus, and the first this number we haven't numbered this. Okay, so this is, let's give it some alphabet, let's say b. Okay, or whatever, or directly what. So y1 into 2 into n1 plus y2 into this number, here it is 3, so y2 into 3 into n2 and y3 into 2 into n3. So y2 into 2 into d5 plus 1 into 3 into 21 plus 1 into 2 into 15. 140 plus 84 plus 30. 254. Right? 254. What had we obtained before? We had obtained 23. Okay.
So,
Yes, yes.
hello.
Speak. I can hear you.
So there will be 63 instead of 84.
Yes. Okay. So again, so we can say that x, that is our x is 233. You can say that x is 233 is congruent to 2 mod 3. Okay. Now one thing, that is like, how do you understand this, the previous result? Okay. So if we can write this as, basically if you see, the point is this is congruence. Okay. So our earlier answer was 23, and our combined modulus, that is capital N, our combined modulus is 105. So this, like it is true for 23, it will be true for 105 plus 23, that is 128, right? And it is true for 23. This is like 23 plus 1 into 105, 23 plus 2 into 105, any multiples of modulus, you can add it, and still it is true. So in that way, you can say that it is, you can understand it in this way, basically. So 23 is congruent to 128 is congruent to 233 mod 105, whatever, wherever you place the bracket, modulo 105. Okay, let's see one more example. Any questions in this?
Excuse me, sir.
Yes.
Sir, can you please speak little loudly?
Okay. Is it better now?
Yes, sir.
Okay. What is 2, 3, and 2 here? So it was there in the previous lecture. The problem statement was that it was like a puzzle, that x is congruent to 2 mod 3. Then also the same number x is congruent to 3 mod 5, and x is congruent to, again the same x is congruent to 2 mod 7. So those are the numbers 2, 3, and 2. Those are given in the question. So your question is basically this part. Where it is. This is your question. So 2, 3, and 2 come from here. Okay. Anyone has any questions yet, or let's see another example. It would be much clearer at that point. Okay. So x is congruent to 2 mod 5, x is congruent to 3 mod 7, and x is congruent to 10 mod 11. You have to solve for x. Calculate n. First step, calculate n. Okay. Second step, calculate n1, n2, n3. So n1 is, okay, so basically you can also write it here for clarity that m1 is 5, m2 is 7, and m3 is 11, and n1 is this n divided by m1 is actually n divided by m1, but as you can observe it is like taking the product of other two moduli. Okay, so this 77 n2 is 55 and n3 is 35. Okay, then what will be the next step? Next step is inverse. Yes, find the inverse. So you have to find the inverse of n1, that is 77. So you have to find the inverse such that 77x congruent to 1 mod m1, that is 5. Okay, now this is not a direct calculation. We'll have to, what will be, or instead of x, the terminology we use here is, can use y over here because x is in the question itself. What is y1? 3. 3 is correct. Okay. 77 into 3 is 231. So y1 is 3. Then similarly find y2. n2 is 55. So 55 y2 is congruent to 1 mod 7. What is y2? This is a little bit, okay, so in exam or in tutorial, you may need to use the extended Euclidean algorithm to solve this. Okay, or otherwise you will have to do trial and error. But so like 51 into 1 mod 7, 55 into 2 mod 7. Yes, 6 is the correct answer. Y2 is equal to 6. Okay, then in 3 is 35. So 35 y3 is congruent to 1 mod 11 m3. Okay, so y3 is 2. 35 to the 70, and we are dividing by 11. So 35 3s are 105, 35 4s are 140, 35 5s are 175. You're dividing by 11, so okay, 175, 210. 35 6 are 210. Yes. 19 11s, 19 multiplied by 11 is 209, and 35 6 are 210. Okay. So we got y1, y2, y3, and now we'll find x. So x is y1. Actually, in the theorem, these are called a's. This is a1, a2, a3. So we can use the terminology. So y1 into a1 into n1 plus y2 into a2 into n2 plus y3 into a3 into n3. y1 is 3, a is 2 itself, 3 into 2 into 77, 6 into 3 into 55, plus 6 into 10 into 35. Okay, what is this? y3 is 6. What is this product? Whatever result of this. 3552 is correct. 3552 is correct. Now what we'll have to do is now this is an answer. This is an answer, but we can reduce it. Okay, we can reduce it again. The not so well. So 3552. How to reduce it? See, the combined modulus is 385, right? 385. So 385 tens are 3850. So 385 into 9. This is your rough work kind of. 5 carry 4. 72, 76 carry 7. 27, 7, 3, 4, 6, 5. Okay, 3, 4, 6, 5. Okay, so 3552 minus 3, 4, 6, 5. If you do, you get 7. 4 minus 6 is 8. 87. So it is congruent to 87 mod 385. Okay, so your answer is also 87. If you can also verify, right? 87 divided by 5, 85, remainder is 2. Mod 7, 84 is the closest one, and 11, 77 plus 10. Okay, so this was all about Chinese remainder theorem and how it is applied. More than the theorem, this method of solving is important because theorem won't be asked in the exam. You don't have to write the theorem. Okay. Any questions? Any doubts? Okay, no questions. So let's proceed. The next thing is Fermat's theorem. Fermat's There are two theorems of Fermat: Fermat's last theorem and Fermat's little theorem. So what we are going to study is Fermat's little theorem. Okay. Actually, just called Fermat's theorem, but not to confuse with last theorem. So it is called as little theorem. Okay. So the lowest, smallest prime number is, okay, let's start with, okay, let's take any general example before going to the theorem. So let's say we'll see the powers of 2. So 2 raised to 2 minus 2 is congruent to dash mod 2. So whatever the power is there here, whatever the power we are raising to, same, the like with respect to the same number we are taking its modulus. Okay, so 2 raised to 2 is 4, 4 minus 2 is 2, 2 mod 2 is 0. Then 2 raised to 3 minus 2 is congruent to what, mod 3. So 8 minus 2 is 6, again 0. Then 2 raised to 4 minus 2 is congruent to what, mod 4. So 16 minus 2 is 14. 14 if you divide by 4, remainder is 2. Then 2 raised to 5, 32 minus 2 is 30. And because power is 5, we take the mod with respect to 5. Okay, mod is again 0. 2 raised, if anywhere you find the calculation incorrect, then stop me. Okay, mod 6. So 64 minus 2 is 62. Remainder is 2. Okay, then 2 raised to 7 minus 2 will go up to 10, let's say, okay, or 11. Okay, so 2 raised to 7 is 128, 128, 126, 126 mod 7 is 0. Again, multiple of 19, 19 sevens are, no, 14, no, 126 is 18 sevens are, right, 18 sevens are. Then 2 raised to 8 minus 2 is congruent to dash mod 8. This is 256, 254. 254 is, what is the remainder? 14, 6 is the remainder. Just verify. Yes, I think. Okay. 2 raised to 9. This is 512, 510 mod 9. 45. Remainder is again 6, I guess. Okay. 2 raised to 10 minus 2 is congruent to, this is 1024, 1022. Simple enough, was what, 10. 2 raised to 11 is 2048. 2048, 2046. Okay, 2046 divided by 11 is divisible. So it is 0 mod 11. Any observations that you can make in this entire calculation? What is your observation in this entire calculation? Odd values. What happens at odd values? It's 2 when power is even. We have 0 remainder. Yes, Hemant. Are you saying something, Hemant? I cannot hear you.
So prime powers are giving remainder 0.
Yes, correct. Yes. Aditya has also said that. Then okay, so whenever the power is prime, the remainder is 0. Okay. We can say that 2 raised to n minus 2 is congruent to 0 mod n if n is prime. Now I'm not saying that only if, if and only if is not there. Okay, there is only if. There is only if, because it can happen in some cases that what I want to say is 2 raised to n minus 2 can be 0 mod n if n, like, only if is not there. It can be there for some other cases as well, but if n is prime, then it has to be 0. If n is prime, it has to be 0. Okay, so I cannot find an easy counter example right now, but only if part is not there. That is what I want to say. If n is prime, then 2 raised to n minus 2 must be congruent to 0. Remainder will be 0. But there may be some other numbers n as well, such that this holds. Okay? But if it n is prime, then it has to hold. So if is there, but only if is not there. Necessary condition is there, but sufficient condition is not there. That is necessary but not sufficient condition. Okay. So formally, okay, the theorem says that uh, for any integer a, any integer a, here it is 2, any integer a raised to p minus a is congruent to 0 mod p. Okay, where p is a prime. P is a prime. Okay. In other words, can say that if we add a to both sides and we divide by a, so a raised to p is congruent to a mod p. If we divide by a on both sides, a raised to p minus 1 is congruent to 1 mod p. Okay, so this is the Fermat's little theorem. Now, how it can be used? So, power of 2 we already calculated. So a raised to p minus 1 is congruent to 1 mod P. This can be useful. So, okay, we have already seen this, but let's say 2 raised to 6. Okay, now the P I have taken is 7. Okay, so P minus 1 is 6. So A raised to P minus 1 is congruent to 1 mod P. Okay, so you can directly calculate that way without having to find what is A raised to P. This is slightly bigger calculation. 7 raised to 22 is congruent to 1 mod. This is A. This is P minus 1. So this must be P. 22 plus 1 is P. So whenever the power is a prime number minus 1, then we can find the modulus. Oh, sorry, I wrote P instead of. Okay, so mod 23. Okay, P is 23. Okay, so let's say I want to calculate 7 raised to 110. What will be the remainder when 7 is 7 raised to 110 is divided by 23? What will be the answer here? 1. Correct. Okay, it's like multiplying this 5 times. So it is 1. Now what if I say 7 raised to 200? Modulus is again 23. What is this? Solve this. From the basic properties of modulus, what is the nearest multiple of 22? Think that way. Nearest multiple of 22 for 200. Nearest to 200. 3. Yes, 3 is the correct answer. But the intermediate step here is uh, 22 nines are 198. Okay, so it is congruent to, you can say, so this is like 77 raised to 22 raised to 9 multiplied by 7 square is congruent to, so this part will go away, so only this will remain, so it is congruent to 49 7 square, and then because it is 23 we can reduce it further to, 23 2s are 46, so you can reduce it further to 3 because you want the exact remainder. This is your answer, this is not your answer, this is your answer. 3 is the answer because you want the remainder as such. Okay, I hope you remember the concept of least positive residue. That is the remainder. Remainder should be between 0 and m minus 1. So 0 to, it should be between 0 to 22 as such. Okay, so okay, any questions, any doubts in this theorem? All of you got 3. Is it understood? Anyone has any questions? Can we take 7 raised to 200 as 7 raised to 199 multiplied by 7 raised to 1? How will that help us? You can unmute and answer.
Hello,
Yes.
sir. 199 is a prime number, so it will go as 1, and then 7 raised to 1.
No, the 7 raised to should be prime number minus 1. Okay.
Okay, okay.
And besides that, our modulus is fixed at 23, so it won't help. Okay. Anyone else has any questions? Okay. Because you're not, I'm assuming that there are no questions. Okay, then the next concept will be Euler's totient function. Okay. Okay, what I'll do is let me put one question to you and let me see if two people can answer because I'm a bit suspicious. Okay, so try to calculate 5 raised to 5 raised to 20 mod 17. Quite simple actually. See, in exam or in plain English, I can also write this as simply write this as, what is the value of 5 raised to 20 modulo 17? If I say what is the value of 5 raised to 20 modulo 17, then also it will mean that you have to divide 5 raised to 20 by 17 and find the remainder. Okay, 5 raised to 20 modulo 17. So any number modulo 17. 6. Okay, I want more people to reply. 8, 6. 13. Okay, better. Okay, let's see. Many answers. Okay, so first of all, by Fermat's theorem, what you can say is 5 raised to p minus 1 is 5 raised to 16 is congruent to 1 mod 17 by Fermat's theorem. Okay. Now 5 raised to 20 means we are multiplying by 5 raised to 4 on both sides. 5 raised to 4 is 625. 625 mod 17 we have to find out. So what is this congruent to? That is what I like. I want to find the remainder when 625 is divided by 17. Okay. So many of you are getting 13 now.
Sir, repeat it again, sir. Please.
Okay. Which part exactly? Up to what part did you understand?
These last four steps, sir.
Okay. So this was the question. 5 raised to 20. I am dividing it by 17. And what will be the remainder? So by Fermat's theorem, a raised to p minus 1. We had written this part here. So a raised to p minus 1 is congruent to 1 mod p. So in this case, 17 is the prime number p. So a raised to a is 5. So a raised to p minus 1 is congruent to 1 mod p. Therefore, 5 raised to 16 is congruent to 1 mod 17. This part is okay. Then up to this part, is it clear? This step is clear, Matin?
Yes, sir.
Okay. Now what I'm doing is I'm multiplying by 5 raised to 4 because I actually want 5 raised to 20 over here. So multiplying by 5 raised to 4, 5 raised to 4 is 625. That is this step. Okay. And now because I want a remainder, so remainder should be something between 0 to 16. So 625 mod 17 is true, but we want something congruent to it, which is within 0 to 16. Okay. So to solve this step, I think for this chapter and this, like you can use calculators obviously, but if you are good with tables, then it will be faster for you that way. Okay. Is it clear, Martin?
Yes, sir.
Okay. So 13 is the answer. 13 is correct. Okay. So next is the Euler's torsion function and Euler's theorem. Actually, what is torsion function? Okay, one more thing is there in Fermat's theorem. Like there is one more condition over here, and that is A should not be divisible by P. P should not divide A. Okay, the number A should not be a multiple of the prime P. This is also a condition. Because then otherwise it will become a trivial case because okay, if A is a multiple then it will always be 0 mod P. That's why we have to add this condition that P does not divide A. A is not a multiple of P. Did you get this condition, what I said? Yes? Okay. So, quotient function is simply defined as the number of if we consider any integer n. Okay, n is any positive integer. Okay, so quotient function is denoted by this. It is equal to, there is no function to write the, okay, so I'll write it. So it is the number of integers j between 1 and n such that GCD of j and n is 1. It is the number of integers that are relatively prime to n that count, number of integers that count is the quotient function. So for example, quotient function of 3. Quotient function of 3. So what all are the candidates? 1, 2 and 3. GCD of 1 and 3 is 1. GCD of 2 and 3 is 1. Therefore quotient function of 3 is 1. Quotient function of 4 is, oh sorry, here answer is 2, because it is true for j equal to 1 and j equal to 2. In case of 4, it is true for j equal to 1, not true for j equal to 2, j equal to 3. Okay, so again it is 2. Are you getting this calculation? The quotient function of 5 is, 5 is a prime, one way of saying that. So it is GCD with 1, 2, 3, 4. GCD with everyone is 1. Okay, in case of 5. So you can say if n is prime, then quotient function is n minus 1. What is quotient function of 6? Calculate.
Excuse me, sir.
Yes.
Sir, can you please repeat?
Quotient function, which part? Definition is clear.
Yeah, definition is clear. With example, one example.
So quotient function of 5. So we will check for integers between 1 and 5. Okay, so we'll check for j equal to 1. It is true. J equal to 2. J equal to 3. GCD of 1 and 5 is 1. GCD of 2 and 5 is 1. GCD of 3 and 5 is 1. GCD of 4 and 5 is 1. Because 5 is a prime, so GCD of every number less than it. If you check it with itself, then GCD will be 5. So 1, 2, 3, 4 will satisfy this condition, and hence answer is 4. So the general statement that I made was, for any prime number, let's say if I calculate for phi of 7, if I calculate for phi of 7 also, then again the same case, it will be the same case. So j, if I start checking from 1, then 1, 2, 3, 4, 5, 6, all of them, if you check the GCD with 7, GCD of 1, 7, 2, 7, 3, 7, 4, 7, 5, 7, 6, 7. Their GCD is 1. So in general, for any prime number, if you calculate the totient function, then it will be n minus 1. Okay. And for 6, as you must have calculated, so with 1, it is true. With 2, not true. 3, not true. 4, also not true. Because GCD of 4 and 6 is, so I'll just write for which cases it holds true. It holds true for 1. In case of 2 and 6, the GCD is 2. In case of 3 and 6, the GCD is 3. In case of 4 and 6, the GCD is 2. In case of 5 and 6, again, GCD is 1. Okay, and again, 6 itself is not there. So, because, okay, so again, for 5 of 6, the result is 2. Is it clear, Akash?
Yes, sir.
Okay. So this is what totient function is. Okay. Okay. Now for the sake of the example, okay, let's also calculate quotient function of 8. And quotient function of 2. We also need quotient function of 2. So in case of 2, answer is only 1. In case of 8, 1, 2 is not there, 3 is also there, 4, no, 5, 6, no, 7, no, 4. Okay, so the result is, okay, one of the results was that, I'll just write it down instead of just orally. So totient function of a prime number is always p minus 1. Okay, and if GCD of, let's say, m and n is 1, if m and n are relatively prime, then totient function of m multiplied by n is equal to totient function of m multiplied by totient function of n. Okay. So in this table, if you see any two such numbers relatively prime, okay, to verify this, we'll have to calculate quotient function of, let's say, quotient function of 12. Let's verify if of 12 is indeed equal to quotient function of 3 multiplied by quotient function of 4. Okay, so for 12, for 3 it is 2, we already calculated, and for 4 it is also 2 calculated. Okay, on this side, j is equal to 1, not 2, not 3, not 4, 5, not 6, 7, not 8, not 9, not 10 and 11. Quotient function here is 4. Thus we have verified this. Okay. Did you get why quotient function of 12 is 4? Yes. 1, 5, 7 and 11. Okay. So now let's proceed. So in that way, okay, there is a proposition. Quotient function of power of a prime number is a prime. Power of prime number is always p raised to k minus p raised to k minus 1. This is a result. This is like a theorem. This is a fact. Quotient function of p raised to k is equal to p raised to k minus p raised to k minus 1. So using this, you can say the quotient function of 2 cube, that is 8, is equal to 2 raised to 3 minus 2 raised to 2. 2 raised to 3 is 8 minus 2 raised to 2 is 4, which is 4. And does 8 have quotient function as 4? Yes. Okay. So calculate quotient function of 200 by using this theorem. Calculate quotient function of 200. This will be the last thing, maybe one more. Calculate quotient function of 200. We'll stop at this example. Just calculate this value and we'll stop. Thirty-two. Okay. So 200 is 25 into 8. We are searching for powers of primes now. Okay. So this is equal to quotient function of, and 25 and 8 are relatively prime. So quotient function of 25 into quotient function of 8. Now this is 5 square. So 5 square minus 5 by this theorem, and this multiplied by, this is 2 raised to 3. So we have already calculated here directly. So it is 4. Okay, it is actually 2 raised to 3 minus 2 raised to 2. Okay. So 5 square is 25 minus 5 is 20. Right? This should be the answer. Yes. Got it? Hemant? Okay. Is it clear to all? Any questions? Any doubts? Anything? Okay, if no questions, I'll end the meeting here.